Second talk of today's session is given by Sergio Valenzuela. Sergio got his PhD in 2001 at the University of Buenos Aires in Argentina, and after that, he held some held research positions at Harvard University and also MIT. In July 2008, he joined the Catalan Institute of Nanoscience and Nanotechnology as professor and as leader of the Physics and Engineering of Nanodevices group. His research is focused on investigating the properties of materials at the nanoscale in different fields like spintronics, but not only, also quantum computation, nano electromechanical system, etc. In particular, in spintronics, he pioneered the study of spin Hall effect using non-local devices, which is one of the topics that he will discuss in his lecture today. I would also like to mention that he was awarded the Ghiambiaggi Prize in 2001 and the UPAP Young Scientist Prize in Magnetism in 2009 for his contributions to the field of spintronics, as well as a starting grant from ERC in 2012. So we are looking forward to your talk, Sergio. You can share your screen and start whenever you're ready.
Okay, can you see the right screen?
Yes,
the full screen one, right?
Yes.
So thank you, Luis, for the introduction, and also I'd like to thank Fernando and Ines and many collaborators that put together this wonderful program, and it's a real pleasure to be part of it and present some specific topic. So the topic I will describe is actually spin Hall effects, as Luis was mentioning. And this is the outline of the talk. I will, for completeness, I will make an introduction on topics that you already heard in the previous days. I mean, just to make a reminder of these topics, because I need them. I will use them in the reminder of the talk. So first, I will make an introduction to spin currents, and then a spin injection and detection in non-local devices. Then I will focus on the spin Hall effects and just the definition, the detection, and some applications, in particular one that are being developed nowadays, and then some new trends on a spin Hall effect, what people are actually doing here. Now, one thing that I learned in the last year with all of these online talks is that for the conferences, it works quite well. I mean, you can give your talk to specialists, and then you talk half an hour only, and then you get the questions. And however, for lectures, I find it much more difficult because I don't have the interaction with the students, and this is essential. And so what I intend to do in this talk is to make it very simple, because I don't know what is getting people, what I understand and what not. And so I will make analogies during the talk. And the analogy is to relate, let's say, a spin with a moving and rotating ball, the football, soccer ball for those in the US. Now, I will try to make this entertaining, otherwise it's going to be very boring. But one thing that I also learned from Fernando is that there were probably much more than 260 participants. Many of them are from Spain, but they are also from other countries, European countries, from Americas, Asia, and Africa. So from everywhere. So I don't want to leave anyone behind. So I want to say that whatever I say about football also applies to tennis, it's applied to golf, it applies to cricket, basketball, but not so much to American football, I must say, because of the shape of the ball, and not at all to pato. So I'm sorry about my Argentinian friends about this. You're going to be left behind a little bit. So let's start with spin currents. To define the spin current, let's go very simple. You have to think about what you know, what people know in general, which is the charge conservation law, or charge currents. And the charge current I define in this way. You have a motion of the charge, and you have the charge which is defined by Q. This is a conserved quantity. The charge current is the derivative of this quantity, so basically it's the velocity of the charge. So you have one electron moving from left to right. That's the charge current. Now you have a conservation law for charge, which basically says that the charge density actually says something that is going to conserve if you integrate over the whole volume. So if you're taking a specific volume here surrounded by this surface, then the derivative of charge density over time will be equal to the divergence of charge current. That's the conservation of charge. You can try to do the same for angular momentum. And if you are in the closed system, that is okay. So you have a magnetization that changes over time. And then you look at how is the angular momentum going away from this surface. And then you have that the derivative is equal to minus divergence of this spin current that you have now. Now, this is not typically a closed system. So you have your angular momentum. The angular momentum of your electrons can go somewhere else. It can go to light. It can go to phonons. It can go to the magnetization of a ferromagnet and so on. So here you always need to add some additional term that is associated to this loss of the spin. Now, if you go back to the definition that I told you before, and then you have the derivative of this quantity. Now here's the spin. And now basically this is not a conserved quantity, so you have the derivative of the product. Before we were talking about this one for the charge current, and this implies that you can have a spin current by just moving the electron, you take the spin with you. But there is an additional situation in which you take one electron spin up moving right, one electron spin down moving left, and you also have a spin current here. This is twice the spin current that you had before because you add this spin current and this spin current. Now, this is definition in some sense of the, I would say, pure spin current that we use a lot on Spintronics, especially to determine spin Hall effects and so on. Now, it is a non-conserved quantity. You can also have this term in which you have the spin that is going to be fixed, but in position, but then you can flip it and then transmit information by changing the orientation of these spins. Overall, of course, this is something that is not conserving the spin, but is taking spin information from one side to the other. One thing I'd like to mention that I find interesting is that if you look at this situation here, you see that there is no charge current, but there is a spin current. Now, if I invert time, you had to take into account that inverting time, you invert the spin, so you do this. And then you invert the orientation of the motion of the spin. So this one that came from right to left, it goes to right. Okay, let me see. It goes like this, and then you go again. You flip, you go again. So you see, if you invert time, you're obtaining the same thing. This is even under time reversal. That means that spin currents can be non-dissipative. So being non-dissipative is on the root of why we want to use Spintronics, right? I mean, it promises to be low dissipation electronics, and basically is hidden in these two ideas here, in which you can transmit information with this spin current that is not dissipative and without moving the electrons that takes the kinetic energy, the bumping into the defects and so on. So here is an analogous situation, also soccer somehow, in which you have the transmission of information in this way. And here's I think I can pass it there. It's a movie. I don't know if you, no, I had to go to arrow. Turn on the pointer. Yep. Here you see. This is something that I took in Barcelona in a game of on a very boring game. Otherwise, people would not be doing that. So let's go, and then you can see that there is some transfer of angular momentum, obviously, on this situation. So now we have if you take a ball and you make it bounce, the charge current is the motion of this. It's the sort of a velocity. It will change sign every time it bounces or it reaches the highest point. And this is a sign of the velocity. Fine. This is very easy. Now you make a you use a spinning ball or you make it bounce in this direction, then you will have a friction at the bottom of when it touches the ball, the surface, and then the ball tends to rotate. So if you have something like this, you make this guy rotate, it touches the bottom, it will rotate in a different direction, it will reach this point and then come back and then so on. Now you have that the velocity goes like this, but then you have a flip of the spin every time it touches the ball. So even though the charge current is like this, the spin current will only change sign when it gets that position only at the top. So you can see that the spin current again is not following the charge current. They go separate ways. The other thing that is important to see here is that this, what I was saying is that if you throw the ball here and it's rotating or not, it will change the motion of the ball. So the linear motion or the orbital motion will depend on the spin in this situation. So this is sort of a spin orbit coupling in some sense, of course, in this very mechanical image. So let's see in this video, actually the actual ball not rotating and start rotate, but because it's rotating in this direction, it gets a friction in this way and it goes the other way. So the way it moves, it depends on the motion. And this is something very important. I mean, you can control the motion of something that is rotated by the orientation of the rotation in some sense. Here's a practical real life image that some of you will recognize 10 years ago or so. And probably the English speakers, the English listeners will not very fond about this. So what I said is that spin current is something that is not conserved. It can be transferred from different places. So if you have a spin current, you can actually generate it from different sources. The sources are those that have a spin angular momentum associated. It could be from mechanical motion, nuclear spin, optical orientation, magnetization dynamics. And we've seen this magnetization dynamics and spin popping, for example. The most used ones are magnetic materials, and also the ones that I will describe later are spin orbit effects. So for going very fast, as this you've seen already, why a ferromagnet can be used as a spin source is based on the fact that you have a two spin channel model. Ferromagnets, you can consider the spin up and spin down as different family of carriers because the scattering of momentum is very quick in comparison to a spin. And so everything that happens with the spin can be considered as after calculating everything that happens with the momentum. So it's an independent channel. The other component that is important is that you have this exchange splitting. And this splitting gives you these difference of the states at the Fermi level, different environment for the spins to move. And that means that the mobility of the carriers at this level, the density of the states are going to be different and so on. So if you apply current in the ferromagnet, then the current is going to be spin polarized. I mean, you will be very unlucky if you have something like this and it's not going to be polarized. You will have a polarization, which is given by this majority and minority spins, a minority and majority here. And this obviously will be between 1 and -1. You can use this as a source of spins. You have a ferromagnet, you put it in contact with something that is not magnetic, you apply a current through it, and it's a concept that I'm going to use. Then you inject the spin polarized electrons that create a splitting of up and down spins, and this will propagate into non-magnetic material. Now, it will not propagate forever because this is not what you have in the equilibrium situation. You will have a lifetime for spins, and this is something relevant, so a spin lifetime, and the signal will decay over spin relaxation length that will depend also on the diffusion of the constant that you have for the carriers. Now you have these devices, which are representative of the giant magnetoresistance. It was discussed on Monday. You can use a ferromagnet as injector, a very thin paramagnet as a way to connect between two. Typically, the current goes ballistic between these, but I represent it in a different way for purposes that you will understand later. But if you have this ferromagnet, you inject these polarized electrons in the intermediate, you create this spin splitting. Now, if you have a 100% polarized ferromagnet, so one of the band is full, then these electrons in this situation where they are parallel, it can go there. But when they are anti-parallel, these electrons cannot go there to the second ferromagnet. So you can change the resistance of these two by changing the orientation of the ferromagnet. And that's the origin of the GMR. This is similar to polarizers, but like two cross polarizers. This you rotate 90 degrees. In this case, it's 180 degrees. You can also have the same kind of behavior if you replace these with a tunneling barrier. The previous one, the GMR devices were used for disk drives, hard disk drives. These also were used for hard disk drives. Nowadays, they are also being used in MRAM, magnetic random access memories. Now I'm going to approach more onto the main part of the talk. So you can use these devices in which you added an additional contact to investigate the spin transport properties. You inject the spins in the middle material. Now these spins propagate, they reach the second ferromagnet in which the currents do not circulate. Now the spins, the electrons can go into the ferromagnet if it is 100% polarized, only if they have the spin orientation that matches the available states here. Otherwise, it will not go. So the electrochemical potential of this guy will lock to this electrochemical potential. If you invert the orientation, it will lock to this electrochemical potential. And then you basically measure a difference in voltage when you switch. These are the kind of devices that you made. And this was described by Felix Casanova. Basically, you have a channel, you have a ferromagnet, you inject the spin polarized electrons, they propagate from these, and then you reach the detector electrode. And then when you reach the detector electrode, you can measure them. You can control the relative orientation of the magnetization of these two guys, that's here. And when you do that, you detect a voltage that will depend on the distance in which they propagated. If you change this, you can measure spin relaxation length. There you go. And this is an example. You have a spin diffusion equation that governs in this system, in many of these systems, the propagation of spins. That gives you an exponential decay. And then if you plot the semi-log, you obtain a straight line. And when you straight the straight line, you can extract the spin relaxation length. It's a parameter that I'm going to use in the next experiment. Another thing that is important is that the use of a spin precession in these devices. So you have that the spin are injected in this orientation, which is given by the magnetization of the injector. Then if you apply perpendicular magnetic field, the spins are going to precess. Under the influence of this magnetic field, they will rotate, they will reach the detector, and then this will measure the projection of these spins along the magnetization. The rotation is given by the Larmor frequency over the time of flight. And then what you obtain is an oscillating signal, shown like that. If you invert the orientation of this detector, well, it just changes sign, it flips. These are experimental results for these devices. And the fact that the signal decreases, it does not change 100, like from the same value from here to here, is that this time is not the same for all the electrons. It's a diffusive process. Eventually, you have full dephasing and the signal goes to zero. Okay, now let's go to a spin orbit coupling. Took me 15 minutes to get here, but I hope it was worth it. So you have that a spin can actually couple to the motion of the carrier, of the electron somehow. And this is done through the spin orbit coupling. Now, the spin Hall effect is an analogous to the standard Hall effect. In the standard Hall effect, you apply a charge current, you have a magnetic field out of plane, let's say, and because of the Lorentz force that this electron field, you will have a charge accumulation at the edges. Now, in the spin Hall effect, it's analogous to this. You apply a charge current, you are under the influence of a spin orbit coupling. The spin orbit coupling, you will see, acts in opposite direction for a spin up and a spin down. And then you basically have a spin accumulation at the edges instead of charge. That's the spin Hall effect. Now, when people predicted this, they did it in a very clever way, a very simple way, easy to understand, by saying, basically, we know that the anomalous Hall effect exists. And this is due to these different mode scattering that you have, but with the presence of polarization in the ferromagnet. You get a voltage here because of this anomalous Hall effect. Now you go above the Curie temperature, you still have this same scattering that take these spins up and down in different directions. So basically you go above the Curie temperature, you should see the same scattering, and then you will have a spin accumulation. And this was predicted in this way by Diacono Perel, again rediscovered by Jorge Hirsch in several years later, like 2 decades later. And Jorge Hirsch actually put the name spin Hall effect. The idea here is that at the time there were a few experiments that were possible to be done, and it was in semiconductors. They were done at the time. They were related to this, but at this time we have a much more capability to do experiments on nanoscale and investigate this much more. So this got a lot of attention. Now let me tell you, at least qualitatively, why you get this separation for a spin up and a spin down in the case of skew scattering, scattering by impurities. Now suppose that I took this from Axel Hoffman talk. So if you have a nucleus, it's positive. So this will create an electric field. Now, if the electron has a magnetization in this direction, I'm plotting the magnetization, not the spin, but opposite. So you have a magnetization in this direction. If it moves in that direction, it will feel the presence of the electric field. Now, this electric field, due to the relativistic effect, will appear as an effective magnetic field in the frame of motion of the electron. Now, this magnetic field will make the electron that passes through this gradient of magnetic field, indicates in this way as you go away from the nucleus. The electron will like to go to the higher, this is a magnetization again, it wants to go to the higher magnetic field or where the magnetic field is higher. It will feel attracted to this direction. So you have, if you have a spin up, it will move a little bit towards the left. Now, if you have a spin down, it would like to go towards the right. I mean, for the same reason, it would like to go towards the region in which you have lower magnetic field. So a spin orbit interaction is just the representation of this, sorry, it's a monitor that is turning off. It's this representation of this relativistic effect. Now, this angle here is related to the spin Hall angle that is typically reported in the experiment. Now, if you go on the other side, you will realize that the electric field is the opposite direction. The magnetic field is also the opposite direction. So this guy is still going to the left, and this guy is still going to the right. So you get this separation of a spin up and a spin down, and basically you have a transverse spin current. But this spin current is a pure spin current, as I showed you before. You can have an analogy with the Magnus force, and this is typically nice to see. So you have a cylinder of a ball rotating here, then the velocity of the wind in the bottom is going to be smaller than here. Then you have a larger pressure on this side than this, and then you have a net force going up. And this is, if you do a conformal mapping of these, you get it's why the plane actually flies. You get that the velocity of the air is faster on the top of the wing, and smaller on the bottom, and that lifts the airplane. You get, of course, the analogy on balls, Hawker balls. And I have shown these so many times since 15 years ago. Probably you've seen it already. First, you should have, let's say that you have the greatest player probably of all time, in Messi, because he can do things like this. So he kicks the ball with the left, and then the ball is going to rotate towards the right. And because of this Magnus force, it goes towards the right. So the spin is counterclockwise if you look at it from the top. Now you have this on a different view. Again, it goes towards his right. I have this other guy, it's okay, which is good, but not so good. I have some show here, but I will not spend on this. Not worth it. So, but yeah, he can also kick the ball sometimes. But he's a righty, and the ball is going to rotate in this direction. So it goes in the other direction. This is the consequence of this Magnus force. And you can see the two images simultaneously. Messi goes towards his right and Ronaldo towards his left. So you have the spin Hall effect that I've been describing. It's like these two guys kicking balls towards the right, both of them. And basically, this is Messi and this is Ronaldo. Now, you also have the inverse of this effect. And the inverse of this effect is to have a spin current in this direction. So if kicking balls spin down one way and kicking balls spin up of the opposite way, so you have a pure spin current. You have these guys doing this. And basically here you have a charge current, generate a spin current. You have here a spin current, you generate a charge current, and these are related by the Onsager relation. They are the same, basically. They are reciprocal effects. Now, how do you detect these? Well, there are some proposals that were done by optical means in the original paper, the Diakonover-Perel. This was the only thing that probably could be done at the time. And then in the Jorge Hirsch experiment, it was a little bit more complicated by the electrical. You apply a charge current along this direction on one slab. Then you can generate a spin current here. You put this transverse slab here that makes contact only to the edge. It's a very complicated device to make. And so that generates a spin current in this direction, which, because of the spin Hall effect, will generate the charge current in this direction, and you can measure it. That was the idea. It's a second order effect. Now, there were a simplified idea that was proposed a few years later, 5 years later, in which you, instead of having this one on top of the other, you just flip it. And basically you have charge current here, you generate a spin current in this direction, which then transforms into spin current, a charge current again here, that generates a voltage that you can measure. Again, second order effect to measure the direct and spin and transverse spin Hall effect. So this has been used because of the simplicity. However, over the years, people have been realizing that it's complicated to extract a spin Hall effect in many situations with this geometry, because there could be many other phenomena that can give place to background signals that are basically artifact and mimic the spin signal here. Now, another alternative was proposed by Schufel-Sang a year later from Hirsch work, and used basically the fact that if you apply a charge current here, you generate a spin imbalance at the edges that then you could measure with the ferromagnet in the way in which you use in non-local devices. What is the problem with this is that current can circulate here. There is a stray field. You can have anomalous Hall effect. You can have some magnetoresistance. You can have Hall effect standard here that flips when you flip the ferromagnet. So there could be some artifacts that complicate this measurement too. So in the end, it was the first experiment were done with optics. And with optics, for example, in gallium arsenide, this was the first report together with another report, which I'll show you in the next slide, in which you apply a charge current in gallium arsenide, and then you generate some spin imbalance at the edges, which you detect by Kerr rotation. You detect this by Kerr rotation, and you can basically see the spin density, how it goes from here to here. The nice thing about this measurement is that you apply a magnetic field that is perpendicular to these spins, and the signal goes away, which is basically you induce a precession, and then you don't see any more of this signal. It's just you scramble the spins that you're supposed to see, this kind of experiment. Now, you can also make these structures in where you apply a charge current like that, they will propagate, and you can see that the spin current that you generate can go away from the injection point, as you see in this case. Nicely, you can use the spin Hall effect as a source of spins. And the other experiment that was done simultaneously with the previous one optically, it is using a rather more complicated structure in two-dimensional Hall gas, in which you apply a current here in the Hall gas, you generate the spin densities here. These carriers recombine, they emit light in this LED light-emitting diode structure, and the light carries the angular momentum that was put by the spins that you had there. So this is what I was saying at the beginning. You can transfer the angular momentum from spins to the photons that you emit. And what you see is that if you change, for example, if you look in here or you look in there, then you will see that the polarization, the circular polarization of the light inverts sign. The direct proof that there's a spin density in this case. Now, the one of important application for applications, it is also important to have this electrically. And the electrical detection was done in two ways simultaneously too. One is something that using an effect that was described a few times already, which is a spin pumping. For spin pumping, you put this in resonance with a oscillating magnetic field. You make this guy precess. The precession generates a spin current. The spin current through the spin Hall effect, the inverse spin Hall effect is turns into a charge current, and then you detect the voltage. The other mechanism, and this is something that is also used frequently, is by using these non-local devices, similar to the ones that are introduced at the beginning. And the idea of using the non-local devices is to use a ferromagnet to inject the spin current, because if you look at this situation in which you just look at the direct spin Hall effect, you generate a spin imbalance, and then you will measure no voltage. That was the reasoning to use the ferromagnet to inject. And basically, instead of looking at the direct and inverse spin Hall effect, we directly looked at the inverse spin Hall effect. You inject a spin polarized current, which is large, and we know the orientation of the spins, and we also know the magnitude. And then you generate this spin current with the spins oriented out of plane, and you measure a voltage through the inverse effect, which is equivalent to the direct one that I plotted there. Well, that's basically the idea. You use the standard non-local device, and then you characterize the spin propagation in this material, and then you use the other device here to actually detect the inverse effect, and then you know all of the effects combined, and basically you can check. You have control devices. So this is the measurement that you get in this situation with the direct effect. You apply a current here, and then you measure in the non-local way with the ferromagnet. You can change the thickness of this channel, and then you change the spin relaxation length. That's interesting. You characterize the spin relaxation length also by spin precession. You can also apply a magnetic field out of plane. So you make these spins rotate, because for the spin Hall effect, you want the magnetization out of plane. And then you can see how the magnetization rotates here in this inset. Now for the rotation of the magnetization, you can get this, the orientation of the spins. And then the spin Hall effect will actually measure somehow the component of the spins that are oriented out of plane at this point, which occur in this Hall cross. So you check the spins which have a given orientation of magnetization out of plane, and then they will convert it on a spin current, but they will be proportional to that sine of the angle that I measure independently. So you can do these experiments, and then from these experiments you can see that it's a very good agreement between the sine of the angle and the actual signal that you measure, and from this you can measure the spin Hall effect. Now, this was done originally in aluminum. This is a very long spin line relaxation length, and that's why this Hall cross worked well. But very low spin orbit coupling, the spin Hall effect is tiny. Now, after those experiments, the geometry was changed slightly in the sense that you use a ferromagnet to inject the spin polarized electrons. They propagate on a channel, and then which is low spin orbit coupling, so long distances like aluminum, for example. But then the spin to charge conversion occurs on a material that has a very short spin relaxation length like platinum. And then there you can measure the conversion efficiency. This is, for example, in the case of platinum, the magnetization, you make it rotate in plane, and because the spins you wanted oriented in the interaction to be absorbed and generate this spin signal. And this is why you see when you rotate from this orientation to that orientation. Again, you see this step, and you can quantify the spin Hall effect. And this is done for many materials. And the interest to do this is because you really want to maximize the spin Hall effect. In some situations, you want to maximize the spin Hall effect and keep long spin lifetimes. And this is very difficult to achieve. Typically, in the metals in which you have longer spin relaxation lengths, is because you have low spin orbit interaction, and that gives you very low spin Hall angles. In metallic systems like heavy metals where you have large spin orbit coupling, the spin relaxation lengths are nanometer size. That makes it a little bit complicated. So in any case, this is good for some applications anyways. And then you can see how this signal in that configuration change when you go from niobium, molybdenum, and platinum. You see that the magnitude changes, but also the sign change. Now, the change of the magnitude depends on the scattering mechanisms that you have or the intrinsic mechanisms. And this change in sign is very well understood from the orbital spin orbit coupling, this material. But it's still not so much agreement of the very much of all of the origin on the spin Hall effect on these systems. Now, another thing that you've seen already is that of a spin torque. I mean, this is again a situation of a combination of the conservation of angular momentum. The spin current coming from this ferromagnet has to change if it goes in a different direction when it crosses this second ferromagnet. So this angular momentum transfers somewhere. It goes to the magnetization of this guy. If you do that, this angular momentum is like a torque that makes this magnetization change, precess and switch. Now, you have the opposite effect. And this is like either, this is the equivalent of spin torque, which is easy to understand in this way of angular momentum conservation. And you also have in which wind actually generates rotation, but you also can make this rotate and that generates wind. And so basically, if you make this guy rotate, you will generate a spin current through the dissipation. And this is the origin of the spin pump. It's a reciprocal sort of effect. You go from like a windmill to like a fan. And people have done these exact measurements on these systems. There was some controversy at the beginning because there are two effects combined, but eventually over the years, people understand very well how the measurement is done, and that is consistent with the non-local devices. You can also look at the change in sign in the spin Hall effect on these systems. It's very, very nice to get the spin Hall effect. One thing that I will not get into much detail here is that there are many, many reports of a spin Hall effect. One of the materials that has been studied the most is platinum. And you can see that the numbers of the spin relaxation lengths, spin Hall angle go all over the place. And so this is a difficulty in our field, is that it's not so straightforward to actually get the number for or intrinsic spin Hall effect. Now there are some efforts to look at these quantities by having non-contact detection, for example, by Kerr microscopy. But this can only be applied in a very, very different situation where the signal is very large, like very heavy materials. The issue here is also that it depends on the details of the sample, if being fabricated, and the interfaces and so on. But it has some important applications, and also for detection. I mean, you've seen these spin torques many times, and you spin torques in a different way of plotting it in the previous slide. You have a ferromagnet that transfer angular momentum to this ferromagnet, and that generates a torque and makes a switch and so on. Now, these kind of experiments in which you apply a current in the horizontal way, that generates a spin current also towards the ferromagnet. And that also generates a torque. So if you want to control the magnetization of a ferromagnet, you can also control it with a spin Hall effect. And this is a very interesting application because when you apply a current here, you might damage your junction. Here, you don't apply a current there. And so for reliability purposes, this could be very useful. The problem is that the currents here are still too large in any case. You need larger spin Hall angles. But you have an advantage in comparison to this, is that if you apply a torque in this direction, then you need the spin current that you generate is basically the current for the polarization. In this case, you have the charge current for the spin multiplied by the spin Hall angle. However, in this situation, you have this area, so the total current could be much larger than in this situation, in which the current that you apply here also generates a current there, there, and there, and there, and the area is much smaller. So this is probably an advantage. Now, another interesting idea that you have here is the magneto that can also be applied in the use of the spin Hall effect, is to detect the state of the ferromagnet. And this is used in the magneto spin orbit logic. There's still controversy how useful this could be, but it's an interesting concept in which you measure the orientation of the ferromagnet by using the inverse spin Hall effect. Now, what is done nowadays, and this is the last 5 minutes, hopefully, of the talk. Nowadays, very much of the research is going towards the topological insulators, which are pretty much an analogous, quantum analogous of the spin Hall effect in some situations. For example, I show you this slide. You have an analogous of the Hall effect, which is a quantum Hall effect. It's been known from the 80s. Now, in this case, you have chiral currents for spin up and spin down at the same orientation. Now, in the spin Hall effect, you have this analogous situation in which you have a spin up and a spin down rotating in different orientations. And these are persistent currents that you have in the materials. As I told you, it's non-dissipative, so they can happen. So you have currents that are circulating constantly. The spin current is quantum spin Hall effect. What to do with them is another story, but they are there. So you can actually remove one of these channels by having an exchange field and take the energy higher of one of them. And in that case, you get the quantum anomalous Hall effect. And in this case, you have really no dissipation, because here you can have back scattering between the states, here you don't. And this is very important for metrology. Now, these 2D materials are part of other series of materials that are known by van der Waals materials, like graphene, 2D magnets, the topological insulators I told you, and strong spin-orbit coupling, materials like transition metal dechalcogenized. Nowadays, this guy is very good to transfer spin information, but nowadays what we are doing is to try to combine all of them to get the multifunctional properties. This is no good for spin manipulation. You want to induce a proximity effects or have a material that has the ferromagnetic properties. So you make these combinations. Now, to convince you that this is very popular in the last 10 years, you can go and see these 2 episodes of Big Bang Theory in which these topics are actually discussed. This is all about graphene in the whole topic. This one is about topological insulator, but very briefly. I like this in particular because what you see on the back is actually all true. This shows you how much care they put in actually looking into this, how to make these episodes. And let me try something here. I will basically focus on this guy because the topological insulators are difficult to explain in this talk. And I will let Sheldon to explain. Where is my mouse? There you go. Let me see if you can hear. Otherwise,
Good evening. I'm your guest lecturer, Dr. Sheldon Cooper.
You will see in the back of the screen.
I was expecting applause. but I suppose stunned silence is equally appropriate. I agreed to speak to you this evening because I was told that you're the best and the brightest of this university's doctoral candidates. Of course, that's like saying you're the most important electron in a hydrogen atom. Because you see, there's only one electron in a hydrogen atom. Best and brightest, my sweet patootie. All right, let's begin. Show of hands. Who here is familiar with the concept of topological insulators? Don't kid yourselves.
So that was it. Just basically, I'm not going to talk about that because I don't have time. So let me finish with one thing I wanted to say is that about what to do with band eval heterostructures. And the idea here is that you have these two-dimensional materials, and what you get in this situation is that you can combine the effect of the functionalities of these systems, because you can make heterostructure by stacking them. You combine the semiconductor with metallic properties, insulating, ferromagnetic, and so on. But one thing that is very important is that you can change the properties of the materials because of proximity effects. Proximity effects are very well known in terms of superconductivity in bulk systems, and have been applied in Josephson functions, and now in quantum computing due to this effect, Josephson effect, because this occurs over coherence lengths that can be hundreds of nanometers. Other effects like magnetism and spin orbit coupling, proximity effects are not very well developed in bulk system, and the reason for that is they occur at very short distances. But if you have a material like graphene, and then you put it in a sandwich between the ferromagnet or a high spin orbit material represented here, then this graphene, the Hamiltonian, is going to be modified by their presence, by the proximity effects, and it's going to be very different, and it's going to have very different transport properties. So the nice thing about graphene is that you can have the Hamiltonian modified by additional terms from top and bottom. And some of these terms can be spin orbit coupling. And this is the kind of thing that we've been studying and other people have been studying in recent years in relation to the spin Hall effect on these structures. And so you can have a graphene, very low spin orbit coupling that you can investigate with this massive Hamiltonian, the propagation of spins over long distances. But then you can use a transition metal decacogenide, which is semiconducting. And with a semiconductor, you can open it. You have a band gap, which is rather large, a couple of electron but you also have a large spin orbit terms in which you have in the K and K prime points, you have a spin splitting that can be hundreds of milli-electron volts, and that alternate in a spin out and spin down bands, like I show here. Now, if you put graphene on top of this, it's being calculated that you can have you're transferring this spin orbit coupling into the graphene, and you get a similar band structure around the charge neutrality point. And this is due to a spin orbit coupling, which is transfer from the transition metal decacogenide, which leads to this splitting and up-down spins in the different valleys. But also you have a rush by spin orbit coupling due to this broken symmetry out of plane. And that actually gives place to two effects in which you convert a spin to charge or charge to spin. One is the inverse spin galvanic effect I didn't mention on this talk too much, in which basically is due to the Rashba effect and the chiral spin texture that you get in these bands, as I plotted here. If you apply a current here, you populate more these states and depopulate these ones, and then you generate a spin density in this direction. That's a way to transform a spin to a charge to spin. If you generate a spin density, it will generate the charge current also. Now you also have the spin Hall effect, as I told you. And these kind of things are measured in these structures. It was done in the group of Felix Casanova. It was also done in a Van-based group. What we did is similar to them. But in this case, we made a more complicated device in which we really verify if this is conducting or not. And so no spin to charge conversion occurs here. And then you can also separate the spin current generated by spin Hall effect and the spin galvanic effect. And the interesting thing that happens in this situation, you can detect it by spin precession. I will not go into detail and separate the two components, is that both of these effects are gate dependent. So you can basically control the spin Hall angle by changing the Fermi level of the graphene. And it can go from large value to something that is smaller if you go far from the charge neutrality point, so this point, or the spin galvanic effect actually can change sign. So you have full control of this effect, something that likely useful to from ferroelectric effect. You can induce this change in the density of spin that you can detect the direction of ferroelectric, for example. It allows you to have other kind of memory devices in this equation. With this, I basically want to finish. And basically, I show you, there is no conclusion on this. I show you like an introduction for spin transport devices. The introduction was what is the spin Hall effect, and also means to detect them, in particular by optical means and also by electrical means. I will let Andrew Kent to talk about the spin orbit torques and all that you get from the spin Hall effect. So thank you for attention.
Thank you very much, Sergio, for your very nice talk. So you managed to explain quite complex phenomena in simple terms, which is quite nice. I have to say that I found the sports analogies very illustrative. It's football.
I hope that people didn't see it so many times already. It's not the first time I used it.
Okay. So yeah, we have some questions and we have about 10 minutes. So let's go through the questions. So the first one is from Julian Zúñiga. If an electric field is applied perpendicular to the plane of the magnetic insulator semiconductor for a spin valve, either current in plane or current perpendicular to plane, what happens to the TMR? Does it increase or decrease?
For the TMR in a semiconductor?
Or magnetic insulator, yeah, magnetic insulator.
So if a perpendicular magnetic field is applied in the magnetic insulator, if the TMR changes.
That's right.
So typically, a first order will not change that much. I mean, so perpendicular to the whole stack is what they mentioned, or?
He says perpendicular to the plane of the magnetic insulator, but yeah, either in a current in plane or perpendicular to the plane spin valve.
The magnetoresistance. So you will have a change in the resistance for this. The thing that is going to happen is that the magnetizations are going to rotate, and that will give place to a different magnetoresistance. The rotation will likely be different for the two ferromagnets because they are different ferromagnets, and that will give you a magnetoresistance. But in essence, it's going to be the same that you have when you switch from one side to the other. In this case, you will have something like this, and will give you magnetoresistance. I don't know if this is going to answer. Probably just reinterpreting the question in some way that fits me.
I think it's okay. So next question from Rafael. He would like to know what is the difference between spin Hall effect and inverse spin galvanic effect?
Yes, there are actually two different effects. So the spin Hall effect, it comes from either in the case I explained, it comes from the scattering by skew scattering by impurities. This is the simplest way to imagine, but also you can have intrinsic spin Hall effect coming from the band structure. And this is basically, you apply a charge current, and due to the spin orbit coupling, you generate a spin current. What you generate is a spin current. Now, in this inverse spin galvanic effect, you have the like a chiral in this situation that I show you, a chiral spin density that is like that. And when you apply a current, you tilt the filling of these bands. And this does not create a spin current. It creates a difference of the filling, which creates a spin density. So the phenomena are different. So you create a spin current in one case, you create a spin density on the other.
Okay, thank you. Let's move on. Next question from Sriram. It's on spin pumping. There are papers talking about real part of spin mixing conductance is damping-like torque, and the imaginary part is field-like torque. Can you shed light on this?
Imaginary part, and the imaginary part is field-like
damping like. Sorry. Real part is damping-like torque. Imaginary part is field-like torque. Sorry.
Yeah. Okay. So the mixing conductance is in the spin pumping actually tells you how it is the spin current going through the interface. Basically, this is what it tells you. The relationship between a spin pumping and a spin torque, in my opinion, is a little bit finicky. I mean, and I will let Andy in the next talk to get to this point with more detail. I mean, the situation is that happen that you see different things on a spin pumping that you see on a spin orbital. They are not really comparable, these two measurements.
Okay. So another question. Please comment on spin backflow in spin pumping. Does it have any significance in spin current absorption by the heavy metal?
Yes, this is related also to the spin mixing conductance. How much of the current is reflected at the interface, and it has this is part of the problem in to interpret the result of a spin pumping is that you need to know precisely the spin mixing conductance. If you don't know the spin mixing conductance, then you don't know how much spin current you are generating into the heavy metal. And if you don't know that, then you can overestimate or underestimate the spin to charge conversion. So it's very important to know this. So the reflection is associated to the spin mixing.
Okay, let's see. So Simone is asking, can you say something about the strength of the spin Hall effect and the spin galvanic effect? What are the conditions for one to dominate over the other? It's related to the previous one.
So this is directly related to, there are two different effects, right? I mean, in the way I explained it before, you have that the spin galvanic effect is associated to how the spins are populated in the bands are populated, or how it is a spin texture in the system. Now the spin Hall effect can depend either on the skew scattering, it can depend on the Berry phase of your system. Different effects. Now, in the case I show in graphene, you can estimate this by looking at how the bands are going to be filled for the spin galvanic effect, and then the change in sign is simply due to the change from electrons to hole, because the spin texture is the same for the top and the valence and the conduction bands. For the spin Hall effect, it's something that comes from the in reality, we don't understand very well what's going on, but you can explain the results, at least the shape that you see, by the intrinsic effect, which should not be working actually on this system. But it depends on system. That's a short answer. It will not be like you have a spin Hall effect, then you expect a spin galvanic effect or inverse spin galvanic effect of this magnitude, and you can control it in different ways. They're different.
Another question from Rafael. Is it possible to have a spin Hall effect in magnetic materials? How does it affect the magnetization?
Yes, you could have a spin Hall effect in magnetic materials. That's for sure. Yes, and you can have intrinsic spin orbit interactions that you have in ferromagnetic materials, and even a local density of state generated in anti-ferromagnetic materials, and this probably is going to be discussed in the next few talks. And this can also affect the magnetization for sure. You could control the magnetization even of an antiferromagnet by having a spin orbit related effects on the system.
So I want to thank Sergio for your talk, and also Yvonne again for participating and sharing your knowledge with us.